Before I get into this, I need to clarify exactly what that headline means, because signals from deep interstellar space sounds a lot more mysterious than what's actually happening, and I don't want to mislead you. NASA has not detected some unknown transmission from beyond our solar system. What's actually true, and what's genuinely remarkable once you understand it properly, is that Voyager 1 itself, humanity's own spacecraft, has been picking up something real out there. A persistent, continuous hum in the fabric of interstellar plasma that nobody expected to find, using an instrument that's now nearly 50 years old. This is the real story of what Voyager 1 is actually detecting in interstellar space, why NASA had to shut down one of its remaining working instruments just a few months ago to keep the mission alive, and where things genuinely stand with humanity's most distant spacecraft right now in 2026. If you want accurate space reporting instead of manufactured mystery, subscribe now, because this story is still actively unfolding. Let's start with what interstellar space actually means for Voyager 1, because the spacecraft didn't simply fly off into some generic void. On August 25th, 2012, after a journey lasting 35 years, Voyager 1 crossed the heliopause, the outer boundary of the vast magnetic bubble our sun inflates around the entire solar system, known as the heliosphere. Crossing that boundary made Voyager 1 the first human-made object in history to leave the direct influence of our sun and enter true interstellar space, the region between stars, filled with an extremely thin, sparse collection of ionized gas called plasma, left behind by the deaths of massive stars in our galactic neighborhood millions of years ago. Every previous spacecraft in the history of space exploration had made every one of its measurements from inside that solar bubble. Voyager 1 became the very first instrument ever to actually measure what exists on the other side. That's where the genuinely fascinating part of this story begins, because starting in 2017, Voyager 1's plasma wave instrument began detecting something researchers hadn't seen before, and it took a specific piece of detective work from a young researcher to properly understand it, Stella Ocker, working with data from Voyager 1's plasma wave subsystem, an instrument that essentially listens for oscillations in the surrounding plasma using two long antennas extending out behind the spacecraft, noticed something unusual buried in the data. Previously, Voyager 1 had only picked up occasional dramatic bursts of plasma activity, essentially momentary whistles, triggered by outbursts from our own sun rippling all the way out to interstellar space, events that happened roughly once a year, giving scientists only a sparse, occasional snapshot of the plasma density surrounding the spacecraft. Looking more closely at the data sitting between those dramatic bursts, Ocker found something that had been quietly there all along, a weak but nearly continuous signal, faint enough that it had previously been lost in what looked like background noise. If a story built on real, verified NASA and JPL reporting instead of manufactured mystery is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. Ocker called this new discovery a plasma wave emission, and unlike the rare, dramatic bursts scientists had already been tracking, this fainter signal turned out to be nearly constant, allowing researchers, for the first time, to build something close to a continuous, ongoing measurement of interstellar plasma density, rather than relying on sparse, occasional events scattered a year apart. As Voyager 1 continued its journey deeper into interstellar space, the specific tone and frequency of that persistent emission would rise and fall over time, and researchers realized that pattern itself was directly tracking how the density of the surrounding interstellar plasma changed as the spacecraft moved through different regions. It's genuinely worth appreciating what that actually represents. For the very first time in human history, scientists had a running, continuous measurement of what conditions are actually like in the space between stars, gathered not through theoretical modeling or indirect inference, but through direct, ongoing detection by an instrument physically sitting out there. If you found this as fascinating as I did while researching it, drop a comment and let me know. It genuinely helps me figure out what to cover next. It's worth being precise about what this plasma wave emission actually is physically, because that's the entire point of correcting the misleading framing at the start of this video. This isn't a signal in the sense of a transmission, a message, or anything resembling communication. It's the natural oscillation of charged particles in the extremely sparse plasma filling interstellar space, essentially the physical vibration of that ionized gas itself, picked up by Voyager 1's own sensitive antennas the same way you might pick up the natural resonant hum of a large, mostly empty room. NASA's own description of the discovery compared it to Voyager 1 functioning like a life raft dropped from a much larger ship, our own solar system's heliosphere, now determined to survey the currents of the wider ocean surrounding it. Some of what Voyager 1 detects still reflects the wake of our own solar system's influence rippling outward, but the deeper it travels, the more it's expected to pick up disturbances originating from sources considerably farther out in the galaxy itself. It helps to understand a bit more about the actual instrument responsible for all of this, because the plasma wave subsystem is a genuinely elegant piece of 1970s engineering that's still doing exactly what it was built to do, nearly 50 years later. The instrument relies on two long antennas, each extending about 30 feet or 10 meters out behind the spacecraft in a V-shaped configuration researchers have informally nicknamed the bunny ears. As the extremely sparse plasma surrounding Voyager 1 oscillates, those antennas pick up the resulting electric field fluctuations, and the frequency of that oscillation directly corresponds to the density of the surrounding plasma, a relationship rooted in basic, well-understood physics. Denser plasma oscillates at a higher frequency, sparser plasma at a lower one, meaning the instrument doesn't need to physically touch or sample the plasma directly at all. It simply needs to listen to how the surrounding charged particles are naturally vibrating, translating that vibration into a genuine, quantifiable density measurement transmitted back across billions of miles to Earth. Now let's bring this story fully up to date, because 2026 has been a genuinely difficult year for Voyager 1, and understanding exactly what's happened recently matters for understanding how much longer this mission can realistically continue. Voyager 1 runs on power generated by 3 radioisotope thermoelectric generators, devices that convert heat from the natural radioactive decay of plutonium-238 into electricity, and that power supply has been steadily shrinking by roughly 4 watts every single year since launch, with no way to replenish it. In late February of 2026, during a routine roll maneuver, engineers detected an unexpected drop in the spacecraft's available power, bringing Voyager 1 dangerously close to triggering an automatic safety mechanism called undervoltage fault protection, a self-preservation system that would have shut down critical spacecraft functions and required a risky, multi-day recovery process to reverse, conducted, as with every command sent to Voyager 1, across a communication delay that now stretches past 23 hours each way. To stay safely ahead of that threshold, engineers at NASA's Jet Propulsion Laboratory made the difficult call to manually retire one of Voyager 1's remaining working instruments before the situation could force their hand. On April 17, 2026, the team sent commands shutting down the low-energy charged particles experiment, an instrument that had been operating almost continuously since Voyager 1's 1977 launch, providing nearly 49 consecutive years of data on ions, electrons, and cosmic rays, and playing a critical role in helping scientists understand pressure fronts and shifting particle densities in the interstellar medium. Kareem Badruddin, Voyager's mission manager at JPL, was direct about how the team viewed that decision, stating plainly that while shutting down a working science instrument is not anybody's preference, it remained the best option available to keep the spacecraft itself operating for as long as possible. That leaves Voyager 1 with exactly 2 functioning science instruments as of right now, a magnetometer measuring the magnetic fields of the interstellar medium, and the plasma wave subsystem responsible for detecting exactly the persistent emission covered earlier in this video, still quietly listening to the density of the plasma surrounding the spacecraft. Both instruments, according to NASA's own statement following the shutdown, continue working great, still sending back genuinely unique data from a region of space no other human-made object has ever operated in. It's worth noting that Voyager 1 isn't actually alone out there in interstellar space either, even though this video has focused specifically on it. Its twin spacecraft, Voyager 2, launched just 16 days earlier in 1977, but took a longer, more complex route through the outer solar system, becoming the only spacecraft in history to fly past all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, before finally crossing its own heliopause and entering interstellar space in November of 2018, roughly 6 years after Voyager 1 made the same crossing. Voyager 2 approached that boundary from an entirely different direction, giving scientists a second, independent vantage point on the same fundamental transition, and its own instruments detected broadly similar plasma behavior once it crossed over, helping confirm that what Voyager 1 had been measuring wasn't some unusual quirk specific to one particular direction out of the solar system, but a genuine consistent property of the interstellar medium itself. As of right now, Voyager 2 still carries 3 functioning science instruments, one more than Voyager 1 currently has running, a difference that directly reflects why engineers chose Voyager 2 as the safer test subject for this year's experimental power-saving procedure. There's a real attempt underway right now to try to buy this mission more time, and it carries a name that sounds almost too dramatic to be real. Engineers have been working on an experimental power management procedure they've nicknamed the Big Bang, an attempt to reconfigure how the spacecraft's remaining power gets distributed across its systems in order to squeeze out additional usable electricity from components currently running less efficiently than they could be. Because the procedure is genuinely untested and carries real risk on a spacecraft this old and this far away, the team made the decision to attempt it first on Voyager 1's twin, Voyager 2. which currently has slightly more power to spare and sits somewhat closer to Earth, making it the comparatively safer test subject. Those tests were planned for May and June of 2026. If they succeed, the team intends to attempt the same fix on Voyager 1 no sooner than July. And if that also works, there's even a genuine chance the low-energy charged particles instrument shut down back in April could eventually be switched back on. Meanwhile, Voyager 1 keeps moving steadily outward regardless of any of this engineering work happening back on Earth. And the numbers involved are becoming genuinely difficult to hold in your head properly. As of the most recent tracking, Voyager 1 sits roughly 15.8 billion miles, or about 25.5 billion kilometers, from Earth, traveling at approximately 17 kilometers per second relative to the Sun, the same trajectory it's held since its final planetary flyby, past Saturn, back in November of 1980. At that distance, a radio signal traveling at the literal speed of light now takes more than 23 hours to complete a one-way trip between Voyager 1 and NASA's Deep Space Network antennas here on Earth. Here's the detail that genuinely helps put that distance in perspective. By the time any single message from Voyager 1 actually reaches Earth, the spacecraft itself has already traveled roughly 1.4 million kilometers further along its own trajectory, meaning the data arriving at a receiving antenna on any given day was actually emitted from a position Voyager 1 left behind more than 1 million kilometers ago. According to NASA's own projections, cited by Voyager project manager Susie Dodd at JPL, Voyager 1 is expected to cross a genuinely historic threshold in November of 2026, becoming the first human-made object ever to sit a full light day away from Earth, a distance of roughly 25.9 billion kilometers, meaning a message sent to the spacecraft and its reply would together take a full 48 hours to complete a single round trip. It's worth understanding why scientists consider this specific kind of data so scientifically valuable, beyond simply being remarkable that a 50-year-old spacecraft can still gather it at all. The heliosphere, the same magnetic bubble Voyager 1 left behind back in 2012, acts as a genuine shield, deflecting a significant portion of the high-energy cosmic radiation that streams in from distant, long-exploded stars elsewhere in the galaxy, radiation that would otherwise reach the inner solar system, including Earth, at considerably higher intensity. Understanding exactly how dense and how variable the interstellar plasma pressing against that shield actually is, something Voyager 1's plasma wave measurements directly provide, helps researchers build far more accurate models of how effectively that shield actually functions, and how it might behave differently as our solar system continues moving through different regions of the galaxy's interstellar medium over time. It's a genuinely rare case, where data gathered from the most extreme edge of human exploration connects directly back to understanding conditions that matter here at home, even though the connection isn't always obvious at first glance. So, what does all of this actually add up to? Voyager 1 hasn't received any kind of mysterious transmission from deep interstellar space, and NASA has never claimed otherwise. What it has done, consistently since crossing into interstellar space back in 2012, is detect the genuine natural oscillation of plasma filling the space between stars, first as rare, dramatic bursts, and then, thanks to Stella Ocker's careful analysis, as a persistent, nearly continuous emission that's given scientists their first real, ongoing measurement of conditions in a part of the universe no instrument had ever directly sampled before. That mission is now genuinely running up against the limits of its own power supply, having just lost one of its longest-running instruments this past April after coming uncomfortably close to a serious fault back in February, with an experimental fix currently being tested on its twin spacecraft in hopes of buying a little more time. There's something worth sitting with in the specific timing of all of this, because it's easy to treat Voyager 1 as a settled piece of history, a mission whose major discoveries all happened decades ago. The reality happening right now in 2026 is considerably more precarious and considerably more current than that. Real engineers are actively working this year on an untested procedure to keep a nearly 50-year-old spacecraft transmitting a little longer. Real scientists are still analyzing data arriving from an instrument built before most of them were born, still finding genuine, previously unrecognized patterns buried in its readings. And Voyager 1 itself keeps moving outward regardless, 1.4 million kilometers further with every single exchange, heading toward a genuinely historic milestone later this year, whether or not the power-saving fix currently being tested actually works. If stories like this, the accurate version rather than manufactured mystery, are what you come here for, subscribe to this channel and turn on notifications. Because Voyager 1's story isn't finished, and there's a real chance the Big Bang procedure changes what comes next. Thanks for watching, and I'll see you in the next one.